Okay, so hello everyone. I'm Rafael, and today we have a very special guest. It's Hudson Mendes. I met him in Belfast, Jug here in Ireland, and Hudson is a top developer. He's been working with software development for 18 years more, so he has a vast experience, um, and he's a technical lead in Aikido.
That's right, yeah, Aikido.
Not to say this name, but it's the company he works here. Currently, he's working in Belfast, and he's also he gave a talk in the Belfast Jug, and he's also now an organizer in the Belfast Jug, and he's also an open source contributor. And one thing that he said to me that he is now, he's an inventor. So he's inventing really cool stuff in the company he's working now. So yeah, hi Hudson, it's amazing to have you here.
Thank you very much, Rafael. Yes, the inventor part, I think all of us are a bit of an inventor. It's just because my name came in a patent. So yes, I'm very proud to say that. Okay, hi everyone. It's a pleasure to be here tonight. Yep. I think the introduction that Rafael gave was fantastic. So nothing much to add. I think we can go ahead and jump into the presentation. Yeah. So
Okay.
share my screen here.
Okay, now the show is yours, Hudson.
Thank you. Okay, so let's talk about vectorization. What it is, where it helps us, and what's the importance of that for, especially for artificial intelligence. Okay, so before I start, thank you very much, Java, for the opportunity to be here tonight. I am a Belfast Chug organizer, so I help in the organization of the Belfast Java user group here in Belfast. But this is a partnership between the two meetups, so it's a pleasure to be here. Thank you very much. So, okay, what's the importance of vectorization for deep learning, right? So to understand why in deep learning we use so much vectorization, we have to understand a few concepts. But probably the best way to start is to understand what an image is for artificial intelligence, right? So whenever you look at this image here, you will immediately notice some things. A few of them is that there's colors, there's shapes, and the human eye is quite good for detecting these features there. But a computer understands numbers, so it's different to understanding the shapes that we do. So we take a much higher level approach understanding an image. But the computer needs numbers. So how can we help the computer to understand an image so we can actually do some cool stuff with it? First thing we do, we decompose the channels. So it's a very very famous way of decomposing the channels is the red, green, blue channels. There is other channels as well. There's other ways to decompose the image, but the red, green, blue is something we, especially in computing, we know for very long. After we do this, we have to understand that each of these points in the image, they are also pixels. So if you're actually looking at a table of pixels there, each of these cells is very small, but it's a table with hundreds of pixels. So when you look at this as a matrix, as a table, that's what you see. It's basically these three separate tables with intensity of the colors, so blue, green, and red. And in AI, especially, whenever you're going to try to process those things, we have to transform these matrices in something we call a feature vector. So we get these three channels, then we just basically stretch them all and put them all together. So we stretch them and put them all together. It doesn't matter to me at this point, or at least in the processing terms, if I'm talking about the blue pixel and the top right corner. So what matters is that in position 50, that's the pixel I have. So all I do is I stretch these tables and make them in a single array. So this image has now become an array. Let's say, for example, a 64 by 64 image. Because I have 3 channels, my array is going to have 12,000 positions. Right? So one image is one feature vector. 1,000 images, 1,000 feature vectors. So we're then talking about 12,000, an array with 12,000 positions, and now we are adding columns, so it's an array of array, 2-dimensional array, and you end up with this, 120,000 items in your matrix. If we're talking about 64 by 64 images, which are tiny, they're minuscule compared to the other images we have nowadays, it's already 12,000 positions. So if you're talking about 1,000 by 1,000 pixels image, you're talking about 3 million positions in your array. So if you're processing 10,000 arrays for learning, for example, there you go. I mean, you have billions and billions of positions. And that's quite demanding for the processor. The CPU actually has to do a lot of work there. So just to give a little bit more context, for neural nets, image processing is traditionally done using a convolutional neural net. This is more or less the mathematics that we have to do there. So it's a sigmoid activation here. There's other activations, but it's a sigmoid function applied on this function here. So you have x times weight transpose plus biases. So this calculation here goes into the sigmoid function, which is basically that thing over there in Java. It's a bit broken. There's a parenthesis missing here, but it's that's the formula. But the most important part here is that the x is a feature vector. So the vector that we were talking about before, that's where it goes. The weights transpose are also vectors. So and the biases are vectors. So all these items there, they're not numbers. They are vectors. So which one of these will have 12,000 positions, right? So when you do it, you're talking about very large vectors. You're talking about matrices and 2-dimension vectors, which are very, they're really huge. And then we come to the need of vectorizations. Processing these large vectors with numbers, we need something smarter to process them. Because if you just go into for loops, you kill your CPU and it takes forever to process. So vectorization is what we do in order to perform these very large vector operations. And that's the importance of vectorization for deep learning. Now, to exemplify what the synced operations are, right? On the left, you see a SISD, single instruction, single data operation. So what you have in the middle is in blue is the CPU, then it's sending a single instruction, single piece of data, and then you have a single result. On the right-hand side, you're going to have a single instruction, and then the data that comes in is in batches. So you're sending this single instruction as saying, for example, multiply, and then you send all this data that has to be multiplied at once. And then it performs all these operations. It saves the instruction every time processes. So your throughput's a lot higher. Then how much faster? Right? So we're looking at this drawing here. It looks like a clever idea. Let's see of an example here. In this example, just because I didn't want to spoil the end of the film, I'm using Numpy. So I'm advertising for the enemy there. But this Numpy example, I created a quick benchmark there, just to explain more or less the order of magnitude in terms of difference that we have. So the serial on the left grows from 0 to 400 milliseconds, whereas the vector version on the right, it doesn't grow. I mean, it grows very slowly. So that's how much faster you actually get when you're doing vectorized operations. Okay, let's say now I don't do AI. So I do AI at work. There's things that we do there are AI related in Aikido. But let's say you're not from the AI world. You're probably asking yourself, why do I care with these vector operations? So it's funny to think that these operations here are something very sophisticated, because they are actually the other way around. They are really simple instructions, and the data they're processing is really simple data as well. So it's very likely that this data is something that you find on a daily basis. So when I say single instruction, single operation, or single instruction, multiple data, which kind of instruction am I talking about? So I'm talking about add, subtract, multiply, divide, but also log, exponential, square root, and so on. So I'm pretty sure that everybody here who does software will have to use this function somehow, right? So you're gonna have some data or to divide data. That's unavoidable. So even a simple for loop that does these operations can benefit from vectorization. And when I say multiple data, the kind of data I'm doing here is numbers in general. Okay, native type numbers, to be more precise. If you go into the object land, unboxing and so on, you pay a price. It's really the native types that are gonna be a benefit here. But single instruction mathematical operations in general, and multiple data, numerical data. Okay. And just to exemplify how you can benefit from single instruction multiple data, I just got some examples here. I mean, all these things, they are single instruction, single data. So they all can be turned into a much faster version using SIMs. Okay, so that's a simple reduction algorithm. In this case, doing a sum, but it's a reduction of any type. Can use that. I have here as an example as well, adding two doubles from two different arrays of the same size. For any reason you have to add these two numbers, you can do the same using SIMs. Here is this single instruction, single data example, but of course you can turn that into the SIMs. Here's another one, calculating the Euclidean distance. So square root of the power 2 a plus b. That's another one. I'm only showing here the single instruction, single data to bring that closer to everybody's world. But I'll go into the SIMD operations later when I explain the alternatives we have there. But for now, these are very familiar examples that everybody here probably knows or have used before. Then I have another one here, is just calculating logs of a double dimension, two-dimensional array, which is a matrix in this case. What the single instruction, single data will do is basically get two pieces of data and send an instruction. So if you think about the big O notation of that, you can probably imagine the waste, because given a vector of n size, each one of n receives one instruction. So it's almost like the big O here is 2n. Whereas the big O of the SIMD operations is pure n. You send a single instruction that's trivial, and then you have only the n, which is the size of your vector. That's where you get the gain, exponential gain over time. Okay, so how to do SIMD in Java then? Probably you guys by now can see where you can benefit from SIMD. So how can you do that in Java? So I started researching about it, and I found a couple of answers. There was the one I knew was going to be the obvious one, but I found another answer from the classical AI and the previous generation data scientists. And what they answered to me was, check, the classical scientific computing called Colt. So there is this beautiful Java library made by the CERN. Not sure if everybody heard about the Large Hadron Collider that stays under 4 different countries here in Europe. It's a fantastic piece of engineering and science. So this lab, which is a fantastic lab with a lot of genius people, they created this Colt library. And if you go to their website, you're going to see that they're very happy to announce that they broke the 1.9 gigaflop per second barrier. Right, so the 1 gigaflop is those many operations. So really, really fast processing. Apparently, it looks pretty fast. So, is that a synced library? That's the first question I asked. So these guys are saying they're really fast. Are they synced? So first thing I did, this is the previous version of the code. I hope you guys can see my screen here. There is a code here doing the z-sum, which is basically the sum of all elements in the matrix, using Colt to do that. So that's a Colt library CERN Colt matrix implementation of the dense matrix. And then I did that comparing to the 0. And so let's see how the results of the Java micro harness benchmark results. They were terrible. So when I looked into the serial, I got this average of 65 milliseconds per operation, and the Colt spent 67. So it's even slower than the serial operation. So the vanilla Java beat the Colt by 2 milliseconds there. I'm sure that everybody heard that Java benchmarking is full of problems. It's not easy to benchmark Java, but even though I'm seeing that at least the same they are, right? And when you go there, so not faster than 0, but why? I went digging the code. What I found in the code was vanilla Java. No seam there, no trace of seams. Later on, choose like later, you will see what's the biggest sign there is a seamed operation being run, and this is not seamed, right? So this is just doing this for loops, and it basically does the operation there. This is a z multiplication, though. By the way, it's not a z sum, but it's the same principle, right? There is a linear vanilla Java operation running there. So not seamed. So this Colt library may be fast, but it's not synced. And then I went for the obvious option because I knew the answer was going to be deep learning for J. So when I spoke to deep learning data scientists, they said deep learning for J. Go to deep learning for J. It's a fantastic library, a lot of contributions currently. The community is growing very much, and go for it. You're going to get right. Then when I went using that for a few things, I got another benchmark here just to exemplify. The benchmark here is slightly different. This code here, there was a problem the way it was generating the data. It was taking long to generate the data itself, so it's compromising the results. So I moved that out. The Java micro harness has this stage thing concept. So you can generate the data beforehand before you actually execute the code. So it's more it's a cleaner result. So what I did here was basically run the micro harness. The results I got were those. So I have now, it's half of the time. Like I said, benchmarking in Java has its flaws. It's hard to predict, but if it's taking the other two are taking double time and this is taking half, okay, we have a lead. That looks like it seemed. Then I went digging the source code for deep learning for J, and I found a lot of native. And that is the main lead you have in terms of searching for synced operations. The reason that this native clause is necessary is because you have to pass special instructions to the processor, right? So the synced instructions, they are actually instructions the processor. Most of the CPUs, the current CPUs, they accept seamed operations natively. They have this instruction there, but you have to send this instruction. And Java currently doesn't have support for it. So you have to go past the binary code, the bytecode, and send these instructions directly to the CPU somehow, right? And yeah, we found it seamed and it's done with JNI. So let's see a little bit more about it. Is JNI the only way to do seams currently? The answer is yes. Right, so you get a simple operation here. You're going to have two pieces of data plus an operation that's bytecode that will become assembler at some point as well. But you don't have a vector sum that does the seamed instruction to the assembler, which would look a lot like the one on the right in orange. Of course, this assembler here instruction may be wrong. Can't tell perfectly because I'm not an assembler master, but I can tell you that that's going to become something more like that. So the answer is yes, you need JNI to do seams at the moment. That's a requirement. But is there anything better? JNI, you're going to have to bypass the bytecode. Is that something you want to do? Maybe not. So is there anything better or anything in the radar for that in the future? And the answer is good news. Yes, there's two very good news about it. So the first one is that I had a surprise. When I was running my tests, I run Java 11. And when I run Java 11, the serial results, they were actually pretty fast. I was getting very fast results doing the serial code. So just the for loop with the simple operations, it was doing much faster than I initially imagined it was going to do. And then I went to why is it doing so much faster? And the answer was Java 9 plus. So above Java 9, we have this thing called superword. A superword is being addressed by a couple of scientists called Larson and Amarasai. I hope I'm telling their names right. These two guys from MIT. So just from being from MIT, I can guess these guys are geniuses as well. So they basically wrote about a way to turn serial operations safely into vectorial operations. And what happened is exactly that. By default, in Java 9 or above, the superword thing is there. So as long as you fulfill a list of requirements for these requirements there, so you must not have an OR condition as the loop condition. So you can't if you have an OR, that will not be vectorized. You can't have a non-inline method inside the loop, so you can't go in anywhere outside the loop. You have to be in there with your instructions. There's a few things, and you can't have a loop as a type for your I as well as you go in iterating. Can't have a long, but as long as you fulfill these requirements, the JVM will transform your code in a vectorized version, and that makes your code out of the box much faster. So giving Java 11 a try to get your algorithms faster, it may be a good idea. Maybe if you just run on top of the JVM 11, it must be good. It might be good news for you. For us, it was fantastic. And there's the second good news is that Java is actually, or Oracle is actually working on this project Panama. So I don't think there's an ATA for it, but there's some specs already being done there. The idea is to make, I would say it's a better JNI. They are offering a standardized API to deal with more CPU level instructions and other things as well. So this project Panama will probably make this ability to talk to the processor directly much better, and the seamed operations will very, very likely be benefits by this project Panama as well. Okay, so I would say it's a better native API than JNI. I am no JNI expert, but as much as I could see, there was a lot of complaints about the way JNI works. So I think that's kind of whoever deals with it on a daily basis. Okay. So just before I move out, one comment that somebody asked me in the Belfast jug, and I found really interesting. Does it benefit? Is there any benefit? I'll come back to the presentation in a second. So 2 seconds. Yeah. So is there any benefits in using GPUs instead of CPUs? And the answer is yes. So whenever you're doing a CPU, you have many times you have the benefit of multi-threading, and then you have multiple cores doing the processing for you. But if you're using these multiple cores and sending one instruction, one piece of data, you're still wasting all this time, this processing time with the instructions. So what you can actually do there is just send one instruction and use a bigger bus of the processor. So if you have a 64 bits processor, you're using a bigger bus. When you go to a GPU, on the other hand, it's much better because the bus of the GPU is much larger. So you can send more bits at once. So the data you're sending through at once is bigger, and then you can send a single instruction, and all this data to be processed. This definitely does cause the processing to be a lot faster. Not surprisingly, this came in the GPU, because GPUs process images all the time. The graphical processors, they're especially used to gaming is one of the big things. And whenever you do gaming, you're processing images over and over a lot of times. So that's why these boards were designed to process a lot of very large arrays and matrices. So this is why they're so much better to do this kind of thing. And if you use a GPU, learning goes a lot faster than AI. And that's what we currently do. There is even a different architecture. Google calls it TPU, Tensor Processing Unit. So it has a bigger bus. Amazon has its own design for a GPU. Again, bigger bus. So that's all to use scenes more effectively. So it's all down to how you send the single instruction, multiple data to the CPU, GPU. That's why GPUs are fantastic to do this kind of processing. And okay, back to the presentation here. Okay, that was pretty much what I had to talk tonight. This presentation, the code that I used in presentation that I was showing on the other screen, it's all in this on my GitHub. So if anybody wants to have a look at it, github.com Hudson Mendes, you find the Belfast jug sample 3 there. That's the one with the benchmark. And yep, that's pretty much me, I guess. What next steps, Rafael?
Okay, so yeah, thanks, Hudson. Clearly an amazing presentation where I could learn a lot. And for sure, our audience learned a lot as well. And I'll just ask you if you have any questions. If not now, you can follow Hudson and send him your questions so that he can answer you later.
Yeah. So about that, please do get in touch. Would be lovely to have a conversation about it. I am continuously studying deep learning. So there's a lot of about the scenes and vectorization that I've been going deeper on a daily basis. So it would be a pleasure to talk more about it. If you find me on Twitter or LinkedIn, let me know that you're from Soul Java. It'll be a pleasure to talk about it. And also, yeah, heads up, if anybody is up here in Ireland, please do let me know as well. Send me a message. It would be great to have a pint here and talk about programming a little bit more. And just an open invitation as well. The Belfast Chug often has place for whoever wants to speak about something fun. It would be fantastic to have you guys here. So let me know if you want to show up here and do your talk. We can talk about it later. Reach me out on any of these social networks. There, it will be a pleasure.
That's it. So yeah, if you're coming to Ireland, you can. It's a very good invitation for you. So I would recommend you to come to Belfast Jug. I've been there once and it was amazing. And also, if you want to come here to DubJug, you are welcome. Yeah, so that's it. Thanks very much, Hudson.
Thank you. Yeah.
It was well, a lot of great content. It's amazing for us to be in touch with all this technology and all this knowledge.
Cool.
For me, it was amazing. It was very impressive.
Cool. Yeah, there's a lot of fun stuff. When you go to AI, it's a new ground with a lot of learning there. So if you're bored with the things you know and want to learn something new, deep learning and AI would be a very good ground.
Mm-hmm.
Cool.
So, yeah, nice. So do you have a final message to the guys?
No.
I mean, you have 18 years of experience. It's a lot. So for sure, you have some golden tips, something that would really help developers on their journey.
It would be just to confirm. I saw that So Java ended my transmission here, and I'm not sure if I'm still live on YouTube. Just to double check.
You are live, yeah.
Okay. Okay. So a message to everybody. Well, about that I can tell a lot. So I'm myself a very passionate software engineer. I started in 1999 to give my first steps. And reality is that by then, knowledge wasn't as accessible as it is now. And I haven't even been to university. I learned everything by myself. I started with all the books. I did a lot of C# over the years, Python and Java. And that's, I think if you have love for learning, being in software engineering is the best place to be, because just an endless source of challenges to solve, and it does require you to study a lot. So I'd say, think to yourself, do you like learning? And if the answer is even remotely yes, just grab programming and engineering with your hands, because that's the best area to be, not just today, but I think that in general terms, it's a fantastic area to be. So keep going if you're new, and if you're already being into programming for very long, come to AI Land. It's really, really fun.
Okay. So yeah, powerful message. Keep on learning, never stop learning.
Yeah, that's it.
Okay. So thanks, Hudson, and it
Thank
was amazing to have you here. And yeah,
It was a pleasure. Thank you very much for the opportunity again. Thank you very much. Cheers.
you guys.
Bye.